Welcome to our presentation on quantile regression with Stata. This session is designed to take us beyond the average in our statistical analysis. Traditionally, models focus on the mean, but often the most insightful stories are found at the extremes of a distribution. Quantile regression, especially with the enhancements in Stata 19, provides a powerful lens to explore these critical areas. We'll delve into how this technique allows us to analyze complex phenomena like economic inequality, assess risk, and understand how effects can vary significantly across the entire spectrum of our data rather than just observing a single overall effect. This approach offers a much richer and more nuanced understanding, revealing heterogeneous impacts that average-based models would simply miss. Now, let's explore why moving beyond the average is so crucial.
Standard regression, like OLS, can sometimes lead to a superficial understanding by treating different underlying realities as if they were the same. For instance, two distinct distributions, labeled A and B, can possess identical means, yet their actual shapes and implications are vastly different. In economic analysis, relying solely on averages often conceals crucial information. Consider agricultural risk. It's not about the average yield, but rather the vulnerability to crop failure, which lies in the lower tail of the distribution. Similarly, the returns to education are far from uniform. They differ significantly for low earners compared to top earners, a nuance completely obscured by an average effect. This highlights a critical insight. Ordinary least squares, or OLS, provides a blurry, one-size-fits-all picture that can be misleading. Quantile regression, in contrast, sharpens our focus, allowing us to examine and understand the specific dynamics at the extremes, or tails, of a distribution.
Our decision framework helps us determine when to use OLS versus when to move beyond it. The first crucial step is always to clarify your research goal. If your primary objective is simply to estimate the central tendency or the average effect of variables, then traditional ordinary least squares, or OLS, regression remains a perfectly efficient and suitable choice. However, if your research question delves into analyzing aspects like inequality, risk, or how relationships manifest at the extremes, what we refer to as tail dependence, then you should consider moving beyond the average. In these instances, quantile regression, or QR, is the appropriate tool. It provides a complete, nuanced picture of the conditional distribution, rather than just a single snapshot of the center. Depending on specific challenges, such as endogeneity or small sample sizes, Stata offers specialized QR commands like EViews, bsqreg, or the standard qreg and qsreg for different scenarios. To navigate the diverse applications of quantile regression, Stata provides a comprehensive ecosystem of commands. For standard estimation, we have qreg for basic quantile regression and bsqreg, which is useful for obtaining more reliable bootstrapped standard errors, particularly in smaller samples. Moving to comparative analysis and testing, sqreg is absolutely crucial. This command performs simultaneous quantile regression and is mandatory if you intend to statistically test differences in the effects of variables across different quantiles, for instance, comparing the impact on the lower versus upper ends of a distribution. Stata 19 also introduces advanced and robust methods. Invaluable addresses issues of endogeneity using instrumental variables, while bsqreg offers a Bayesian approach, which is especially beneficial for small sample sizes as it provides exact posterior distributions without relying on asymptotic assumptions. These tools empower researchers to conduct a wide range of nuanced analyses. The fit of any regression model is fundamentally determined by its loss function, the penalty it applies to prediction errors, or residuals. Ordinary least squares, or OLS, uses a squared loss function, which you see represented by the symmetric U-shaped curve. This means that large errors, especially outliers, are penalized disproportionately, heavily pulling the estimated mean towards them. In contrast, quantile regression employs what's known as a check function. This is a V-shaped loss function that penalizes errors based on their absolute value, making it naturally more robust to outliers. The critical innovation is that this V-shape can be tilted. By adjusting the tau parameter within the check function, we asymmetrically weight positive and negative residuals. For instance, for the 90th percentile, it penalizes underpredictions much more heavily than overpredictions. This unique mechanism forces the regression line to fit a specific percentile, like the 10th or 90th, giving us insights beyond just the central tendency. One of the biggest advantages of quantile regression is its inherent flexibility concerning statistical assumptions. Unlike ordinary least squares, quantile regression does not require the error term to be normally distributed, a common issue in real-world economic and social data. This means it can be applied more broadly without violating core assumptions. Furthermore, quantile regression implicitly handles heteroskedasticity. Because it models the relationship across various points of the conditional distribution, it naturally accommodates situations where the variance of the error term changes with the independent variables. This is a property that OLS struggles with and often requires complex adjustments. Finally, quantile regression exhibits strong robustness. It is highly resistant to outliers in the dependent variable. An extreme value in y can drastically skew an OLS mean, but has little impact on a quantile regression line. It's also equivariant to monotone transformations, meaning that if you transform your dependent variable, say by taking its logarithm, the substantive interpretation of your coefficients remains consistent, which is a very desirable property. These characteristics make quantile regression a powerful and reliable tool for complex datasets. The golden rule for interpretation is this. The coefficient beta tau measures the change in the tauth quantile of the dependent variable, y, for a 1 unit increase in the independent variable, x. Let's translate this with an economic example. An OLS model might tell us that 1 additional year of education increases the average wage by $800. This is a single number for everyone. A QR model for the 10th percentile, representing low earners, might find that 1 year of education increases the wage of low earners by only $200. This shows a much smaller return at the bottom. Conversely, for the 90th percentile, or high earners, the same model could show that 1 year of education increases the wage of high earners by $1,500. This clearly reveals significant inequality in the returns to education that the average completely hides. This example clearly illustrates the different stories these two methods can tell. Let's summarize the key distinctions between them. Let's quickly recap the core differences between ordinary least squares and quantile regression. In terms of what they measure, OLS models the conditional mean, or the average effect, of y given x. Quantile regression, on the other hand, models the conditional quantile, meaning it can estimate effects at specific points of the distribution, like the 10th or 90th percentile. For error minimization, OLS uses the sum of squared residuals, which makes it highly sensitive to extreme values or outliers. In contrast, quantile regression minimizes the sum of absolute deviations, making it inherently robust to outliers, particularly those in the dependent variable. Fundamentally, OLS provides a one-size-fits-all view of the data, giving us a single average relationship. Quantile regression, however, offers a view that is tailored to the extremes, providing a much richer, more complete picture of how variables interact across the entire distribution. Think of it like a tailor, fitting the relationship specifically for different sizes of the data. The standard command for quantile regression in Stata is qreg. The syntax is qreg followed by your dependent and independent variables. The crucial option is quantile number, where you specify the quantile you want to estimate. For instance, quantile 0.10 for the 10th percentile. If you omit this, it defaults to the median, quantile 0.5. It is also essential to use the VCE robust option. Since quantile regression is often used in the presence of heterogeneous, robust standard errors are necessary for valid inference. For Bayesian estimation, available in Stata 19, you simply prefix the standard command with Bayes-ents. This approach is particularly useful for small samples because it provides exact inference through credible intervals without relying on large sample asymptotic theory.
While qreg is great for estimating a single quantile, our real interest often lies in comparing effects across different quantiles. This requires a more advanced command, which we'll discuss next.
A common mistake is to run the qreg command multiple times for different quantiles and then try to compare their coefficients. This is statistically invalid because each model is estimated independently, preventing a proper statistical comparison. The correct solution is to use sqreg, which stands for simultaneous quantile regression. This command estimates models for multiple quantiles all at once and, crucially, estimates the full variance-covariance matrix across these equations. The syntax uses the quantiles option, where you list the desired quantiles, for example, 0.25, 0.5, and 0.75. It's important to note that bootstrapping, specified with the reps option, is mandatory for sqreg to calculate valid standard errors. For publication quality results, you should aim for at least 100 replications, often more. So the key takeaway, or pro tip, is to always use sqreg if your research hypothesis involves testing whether the effect of a variable is statistically different across various quantiles, such as comparing the effect on lower income versus higher income groups. Before we dive into any regression analysis, especially with quantile regression, the first crucial step is to thoroughly inspect our data. We need to understand the distribution of our dependent variable, as this informs whether OLS or quantile regression is the more appropriate tool. In Stata, we use several commands for this. Summarize price detail helps us check for skewness and kurtosis. The Glatter price command provides a visual inspection of the distribution's shape, as shown on the right, where we can see how different transformations like log, square root, and inverse affect the visual distribution. Finally, qnorm price generates a quantile normal plot, a formal way to detect non-normality. The key insight is that if your dependent variable is perfectly normal, QR might add less value. But if it's skewed, which is common in economic data, quantile regression offers a powerful advantage to explore effects across the entire distribution. We will now apply what we've learned with a practical example, using the well-known auto dataset that comes with Stata. Our research hypothesis for this practice is to determine if vehicle weight adds value equally across the market. Specifically, we want to know if it has the same effect on cheap, budget cars as it does on expensive, luxury cars. A simple scatter plot of price versus weight, generated with the two-way scatter price-weight command, immediately reveals a classic pattern of heteroskedasticity. As you can observe, the variance of car price distinctly increases as vehicle weight increases. This visual evidence strongly suggests that the relationship between weight and price is not constant across the entire distribution. An OLS model, which assumes constant variance, would therefore be inappropriate here and would likely miss the full story. This clear evidence of a non-constant relationship makes it an ideal scenario for simultaneous quantile regression. Now, let's execute the core regression command. We employ Stata's sqreg command, which stands for simultaneous quantile regression. We're modeling car price as our dependent variable, with weight, length, and the foreign indicator as our independent variables. Crucially, we are interested in three distinct market segments: the 10th percentile for budget cars, the 50th percentile representing the median, and the 90th percentile for luxury vehicles. We specify these with the quantile 0.10, 0.50, 0.9 option. The reps 200 option tells Stata to perform 200 bootstrap replications. This bootstrapping process is vital because it generates statistically valid standard errors, which are absolutely necessary for accurately testing hypotheses about whether coefficient effects differ across these various quantiles. The results from our simultaneous quantile regression are quite illuminating. Let's interpret the coefficients for the weight variable across the different market segments we analyzed. For the 10th quantile, representing our budget car segment, the coefficient on weight is a modest 1.2. This suggests that for cheaper cars, an extra pound of weight adds only $1.20 to the price. However, as we move up the distribution, the effect dramatically changes. At the median, or the 50th quantile, the coefficient rises to 3.4. And for the 90th quantile, which corresponds to luxury cars, the coefficient jumps significantly to 8.5. This stark difference reveals a crucial market structure change. In the budget market, weight has a negligible impact on price, implying it's almost irrelevant. In contrast, for luxury vehicles, weight is heavily rewarded, likely due to its association with premium features, larger engines, and superior materials. An OLS model, by providing a single average coefficient, around 3.4 in this example, would completely miss this nuanced and important story about how different market segments value the same characteristic. After running a quantile regression, we visualize the results using the qreg command to create what's called a quantile process plot. This graph is incredibly insightful. The solid blue line traces the estimated coefficient for vehicle weight across the entire distribution of car prices, from the lowest quantiles to the highest. We can clearly observe this line sloping upwards, confirming that the effective weight on price significantly increases as we move from budget cars to luxury cars. Now, compare this to the dashed orange line, which represents the single, constant coefficient from an ordinary least squares regression. The plot dramatically illustrates how the quantile regression effect deviates substantially from the OLS average. This visual evidence unequivocally confirms that relying solely on an average model for this data would be highly misleading, as the effective weight is far from uniform across the market. This visual insight prepares us for the next crucial step, formally testing these observed differences. To provide rigorous proof of our findings, we utilize the test command after our simultaneous quantile regression estimation. Here, we're formally testing the equality of the weight coefficient between the 10th and 90th quantiles. Our null hypothesis, H0, states that the effect of weight on car price is the same for both cheap budget cars and expensive luxury cars. The output from the F-test gives us a p-value of 0.0031. Since this value is significantly less than the standard 0.05 threshold, we have strong statistical grounds to reject the null hypothesis. This means we can confidently conclude that the market dynamics are indeed structurally different. The average-based model, which would suggest a single effect, is statistically incorrect for describing the relationship between weight and price at these different segments of the car market. To summarize our discussion, let's revisit the core takeaways from understanding and applying quantile regression. First, it's crucial to remember that context matters deeply in economic analysis. Averages, while convenient, often obscure the most vital economic narratives concerning risk, inequality, and various threshold effects that apply differently across a population. Second, the method of quantile regression provides a robust and powerful alternative. By minimizing absolute deviations, it allows us to precisely estimate the impact of variables at specific points of the conditional distribution, offering a much richer picture than a single average. Finally, the practical application in Stata is straightforward, with the sqreg command being essential for simultaneous estimation across multiple quantiles. This, coupled with the test command, enables rigorous hypothesis testing to statistically prove that effects indeed differ across the distribution. As the core message states, use quantile regression when the average simply doesn't tell the whole story.